Start recording.
Yes, I did. So, Bismillah ar-Rahman ar-Rahim. Today what we are going to do is basically go through a revision to the topics that we have covered so far that will be included in our test. The points that we have basically, we are talking about three topics. I'll start by the first one, which is the solar stills. So when we are talking about the solar stills, what you are expected to know is basically how to make an energy balance for different components or different layers. So if I'm going to consider a solar still, sorry. So we have a solar still and we have some water in. Let's say that this is the case that we have at the moment, and there's solar energy falling into it. I think I need to get into the draw, which is essentially G. Then we are basically talking about energy balance. Two different components. The components that we have here for the energy balance are this one, which is the glass cover, and water inside. Sometimes we have this basement of the solar still made of some metallic black painted color, and we call it the absorber, which in many cases actually the idea of operating the solar collectors, especially the flat plate collector that is used for heating water, it should have an absorber, which is a metallic black painted surface that is heated, and then upon its heating, it transfers the heat to the water by convection. For the flat plate collector, it might not only the plate, it could be the plate, and it could be the plate with tubes, which are also painted in black, so that basically the transfer of energy in that case to the water is not by radiation, but it's basically by convection from the hot surface of the absorber to the running water in. In this specific case that we have in front of us, let's consider it. What happens? Let's start by the absorber. The absorber receives energy, it is heated, and then after being heated, it transfers heat to the water above it by natural convection. Definitely, I have to mention that below the absorber, there is another layer, and this other layer is made of insulating material. So, which means that right here, we should have a layer of insulation, not only here, but actually it should cover the whole solar still. So this should be sort of an insulating material which is covering the solar still so that we can reduce the energy loss to the surroundings. And that is an important thing that should be there. Either the solar still itself is made of insulating material like wood or fiberglass, and then you put inside it a layer of metallic black painted surface, which is acting as an absorber, or sometimes people do the whole solar still from a metallic part and they put it all of it inside a wooden box. For us, in terms of analysis, what we are interested in is that each one of these surfaces and the basin or the bottom of the basin is basically covered with an insulating material. Someone had a question?
Yes, Doctor, I have a question.
Yes, go ahead.
The function of the absorber is to enhance the heating of the water?
That's right, exactly.
All right, thank you.
Now what would we need to do is to go an energy balance for these three elements: the absorber, number one, water, number two, and the glass cover, number three. So let's start with the absorber. It's a plate, so I'm going to call it the absorber plate. The equation that we are going always to apply for each one of them is the first law of thermodynamics. That is the rate of energy in minus the rate of energy out is no storage, of course. So this is equal to the rate of energy stored. No generation, I'm sorry. And the rate of energy stored is nothing but m dot, whatever the object that you have into the specific heat into rate of change of temperature with time, or the mass is basically rho into volume, density into the volume, into the Cp, into the rate of temperature with time. So it is this kind of equation that I'm always going to use whenever I'm doing the analysis for any one of the components that we have. And I'm going to use this repeatedly. So let's now get to the absorber plate. I have a plate. This plate is receiving energy from where? Let's look here. Now, this is the irradiation falling into the glass, and then glass is a surface that has its radiation surface properties. Part of it is the transmissivity. So here there is part of the energy that will pass by the glass, which is tau glass into G. Tau is the transmissivity, and it's a property which is always less than 1. If you remember from our study of radiation, that the surface properties are basically alpha, the absorptivity, tau, the transmissivity, and rho, the reflectivity. And the three of them are equal to 1. Which means that, or this originated from alpha G, which is the fraction of the energy being absorbed, plus tau G, fraction of energy that is being transmitted, plus rho G, the fraction of energy that's being reflected, is equal to G, which is the total radiation falling. And that's why the summation of them, alpha plus tau plus rho, is equal to 1. Rho here is the reflectivity, and you should not mix it with the density. That's why I'm not going to use that expression. And I'm always going to use that m dot Cp or m Cp into dt by dt. Okay, so I'm not going to use that expression so that we don't mix between the symbols. Now, we said that there is an amount of energy passing through the glass and falling down. This is tau, transmissivity of the glass, into the radiation falling. This energy, in order to reach the absorber plate, it has to pass through the water as well. So the water itself is going to have its own transmissivity. Accordingly, when I'm looking at the energy in, it should be G into the area into the transmissivity of the glass into the transmissivity of the water. This is what is going to fall into the absorber, but the absorber has its own radiation properties. And the most important one that we are interested in here is absorbing the energy. It's called an absorber. So it should absorb most of the energy falling into it. And that's why we painted it with black, so that it is almost a black surface, so that it can absorb most of the energy falling into it. So alpha plate. So this is the irradiation falling. This is the area, surface area. This is the transmissivity of the glass, because the energy had to transfer through the glass. transmissivity of the water, because the energy has to go through the water to be transmitted through the water and reach for the absorber where it will be absorbed. So this is the kind of energy in that we have here. What about the energy out?
Doctor, this is for the glass, right?
Excuse me?
This is only for the glass.
What is for the glass? I'm talking about the plate now, which is the absorber.
For the okay.
Absorber plate. Energy passed by the glass, transmitted through the glass, transmitted through the water, and absorbed by the absorber. Right? Now, what is the energy out? The absorber is losing energy in two ways. One of them is convection to the water. So H, convection from plate to water into the area of the plate into the temperature difference, T plate minus T water. What is it? This is Newton's law of cooling. And it's written to account for natural convection from this absorber plate to the layer of water on top of it. So this is the one. What else? We have insulation, which means that although there's insulation, what does it do? It reduces the heat transfer rate, but it does not eliminate it. So we have to have some sort of Q losses going through the glass. Say that the insulation is made of fiberglass. Fiberglass does not have zero thermal conductivity. It has 0.0, for example, 35 value of which is the watt per meter Kelvin. So it is not zero. So there is a certain losses, even if the losses are small, just for sake of accuracy, you account for it. So this is, and after that, energy that will transmit by conduction to the insulation is going to be transmitted by convection from the insulation to the surroundings. So I can put it this way. It is the overall heat transfer coefficient of the loss into the area, into the temperature of the plate, minus the temperature around it. Around it, simply, you can put it as T air. So the energy losses from the top, it is losing heat by convection to water. And loses heat through insulation. And finally, the last term is the energy storage, which is some sort of a standard terminology that I write, that M, mass of the plate, Cp of the plate, into D plate by D time. Now here comes the question. When do we account for this storage and when we neglect it? This can neglected if the mass is too small or the thickness is too small. So if I find, for example, that you have a question and it is said that you have a thin plate, then this is a sign that, yeah, because it is thin, then it does not store energy, and accordingly, you can neglect the storage term. The same thing applies for the glass. If the glass is thin glass, then you can neglect the storage term. Otherwise, if you want to be meticulous, if you want to be very accurate, then you would include the storage term. I'm talking about the general terminology. So this is the kind of energy in that comes in from radiation. This is the kind of energy out, convection to the water and conduction, and then convection to the air through the insulating material. And finally, energy storage. If you have a solar still without this plate, then there's no need for all of these equations. Is that clear? You have any questions?
So, doctor, if there are no absorber, then the heat out from the water.
The heat out from the water is going to be this kind of loss, which means that this is going to be T water minus T air through an overall heat transfer coefficient. I'm going to talk about that when we write the energy balance for the water. I will tell you what if there's no absorber, what we are going to do with the water. But normally, for effective operation of these units, we tend to add an absorber. Anyway, if it does not exist, then when we write the equation for the water, I will tell you what differences will it make. Now I'm going to erase this part of the absorber plate, and then we write the balance equations for the water. Now think about it while I'm erasing this part. What kinds of energy N that are going to the water? We have water, which is stagnant there, which is this layer. This layer is receiving energy from the solar radiation which is coming. So there is irradiation coming from the sun into the surface area of the water, into tau glass, because it has penetrated through the glass, is transmitted through the glass. Water is going to absorb part of the energy, so have absorptivity of the water. If we have a plate, then I'm going to account for the heat transfer coefficient from the plate to the water into the area into T plate minus T water. If you remember, we have written this as energy out from the plate in the previous step. Now this energy is going to the water. So when I'm taking the water as my control volume, this is kind of energy in. Suppose that there's no plate, then this whole expression would not be there. So this is the first thing. If there's no plate, then there's no transfer of energy from the water to the from the plate to the water. So this is the energy in. What about the energy out? Water is leaving energy to the top like this. This is when you have a closed part, a closed box, and this closed box is having air inside, we tend to call this as enclosure. Probably you heard that expression when you studied heat transfer, especially convection heat transfer. And because there's air inside, then there will be transfer of heat by convection from the surface of the water to the air. So we have Q, convection, water to the air. Actually, it's not to the air, but the way that we write convection heat transfer expression, we are accounting it from the surface of the water to the surface of the glass through the air. So it will not be very accurate if I just say that it is from water to air. Actually, it's from water, it's going to the glass. But it's just, sorry. So this is convection from the water. Actually, because it's a natural convection in enclosure, so it is going to be from surface 1, which is the surface of the water, to surface 2, which is the surface of the glass. So I can put it like this, from water to glass. Plus Q, radiation from water to glass. Is that important to put radiation here? I know that for the solar stills, it is making use of the greenhouse effect, which means that energy falling into it through the glass is going to penetrate through the glass because the glass is transparent to short wavelength radiation, like solar radiation, but it is opaque to long wave radiation. So what I have inside is long wave radiation. Why long wave radiation? Because it is associated with relatively low temperature, which means that there's no energy that will go out the solar stills. Yes, but inside the solar stills, there's still energy going from the water to the glass. And this energy is by radiation. Why did I write it? Why it's not neglected? Because the mode of energy which is associated to it is natural convection. I can neglect radiation if it is coming from a low temperature source, relatively low temperature source, and I have forced convection. But if I have natural convection, I cannot neglect the effect of radiation. It is small, yes, but the natural convection itself is small as well. So they are basically in the same order of magnitude. In some cases, as you have seen previously when we talked about the solar stills, the value of Q radiation can be even higher than the value of Q convection here. For convection, it is characterized by small heat transfer coefficient. So Q convection, Q radiation, and Q evaporation. These are the energies that are leaving the water. And why I'm changing the color? Because this is based on a condition, Q loss. If I do not have a plate, then water will be losing the energy to the surroundings here. In addition, there is kind of losses from the water to the surroundings from the sides, but this is something that I can safely neglect it because the layer of water is not, depth of water is not big. Accordingly, this distance is something like 1 centimeter or 2 centimeters. So that does not really make a big surface area for convection to occur. But you can consider it if you wish. So that's something that you can consider. It will not be an error if you neglected it because the area is small. So the Q loss through the walls, and it will be also through the bottom if we have no absorber plate. If we have an absorber plate, then you don't account for this. If there is no absorber plate, then there will be losses from the water to the bottom. And then the third expression typically is going to be energy storage, the standard expression M water, Cp water, dt water by d time. So this is the energy balance for the water. Any questions?
Doctor, I have a question.
Yes.
An energy in the part of each plate to water.
Yes.
How exactly it comes? How water absorb energy from the absorber plate?
You have when you are heating water in a container. Suppose that you put a container on the stove and you put water into it. How does water heat? The container is basically metallic. I'm talking about أي وعاء من أوعية الطبخ اللي موجودة عندك في المطبخ. When you put water in and you put it on the stove, تحطه على البوتاجاز على الرينج على الجاس range, what will happen? Water is going to be heated and then it will boil. How it will boil? Because it is receiving energy, it is not connected directly to the fire, but the water is inside the container. So the container walls are going to be heated first and then heat will transfer to the water inside. How it will transfer to the water inside? Basically, it's conduction and convection. Conduction is too small compared to convection, or if you are going to come up with the definition of convection as it is conduction between the fluid particles and advection. So this is what happens, and it's natural convection because water is not moving.
So you mean the capital G here is goes
No,
through the
capital G is what is coming from the sun. This is irradiation. But HP into the area into TP minus T wall, this is basically convection, natural convection from the hot plate to the water. The plate has an absorptivity higher than the absorptivity of the water, which means that the plate is going to be heated to a higher temperature, and then it will transfer its heat to the water. So the solar energy is heating the water, and it is heating the plate more effectively. Then the plate, when it gets heated, it's going to heat the water. Is it clear, Hamad?
yes, good.
Okay. Now, after this, we are going to move to the third component here, which is basically the glass cover. So I'm going to take this out again and get to the glass cover. And again, we'll be looking at what are the energies in and what the energies out from the glass. And actually, we find that when we are moving from one unit to the other, there are some things that are repeated, like energy out from the plate is going to go to the water. Energy out from the water is going to go to the glass. So that's why we solve it as a system of equations. So here we are talking about glass cover. The energy into the glass cover, basically, it has energy coming from the sun. So G, which is the irradiation, falling into the area of the glass. Now I'm talking about the glass itself absorbing energy, so absorptivity of the glass. Plus, what else the energy, whatever energy leaving the water, it will fall to the glass. So it will be Q, convection, water to glass, the same expression that we have written before, Q, radiation, water to glass, and Q, evaporation from the water. So this is the kind of energies into the glass. The energy out, it will be basically Q, convection to the air, and Q, radiation to the sky. Which by sky here, I mean all the surroundings, whatever the surroundings that energy leaving the glass will fall in. Any surfaces surrounding it, then we call it either the surroundings or the expression used to be the sky. And the sky temperature is usually T of the air outside. Some references write it as -6, some other references write it as -11, whatever. This is going to be expressed, radiation here and here are going to be expressed in terms of Stefan-Boltzmann law. Convection is going to be expressed in terms of Newton law of cooling. Whatever is coming to the glass from the water, this is by natural convection. But whatever is coming here by the air, this is forced convection. So air stream, which is coming, blowing wind, it's going to reduce the temperature of the glass. And this is one among the effective ways to improve the performance, because when the glass temperature falls down, the ability of it to condense more water vapor improves. Finally, the energy storage to the glass, which again, you may consider it or you may neglect it. If you assume the glass is thin, you can neglect it. Cp glass, then dt glass by dt. So these are the expressions that we have here to improve the performance. Then When we are considering at what are the most effective parameters that improve the performance of the solar cell, they will be basically, or the most influential or important ones to improve the performance of the solar cell. So to have better performance, the most two influential things here is to have less water. Reduce the quantity of water here. So it will be heated effectively, and definitely the performance is going to be better. And then effective cooling of, effective cooling of glass cover. So by effective cooling, I'm talking about that expression here. If we can improve this, an improvement of that can be, for example, instead of having just wind blowing over the glass, you can have more wind by having a fan, for example, that's going to draw air in a forced convection at a higher speed, higher quantity, so that the heat transfer coefficient increases. Or if you are going to cool this by water, suppose that you are pouring water here, so that's going to have a more effective cooling for the glass, and then the productivity is going to increase. So these are the two most important or influential parts that are, or elements that are going to increase the performance, or if the G increases. So at noon time, you have the highest productivity compared to the early morning and the late afternoon, because basically the value of G is the highest. So this is basically the kind of analysis that you would be required to do when we are talking about solar cells. If you have no questions, that we can further move to the HDH mode of desalination.
Doctor, the first
Yes.
one for the effective parameter is the level of the water.
Level of the water is number 1.
All right.
Followed by the effective cooling of the glass, number 2, and then 3 is the irradiation falling. Khalid?
Yes, Doctor. Question regarding the performance here. So basically, okay, the effective cooling of glass, this would contribute in more condensation of water.
That's
so that
right.
would increase the productivity.
Yes.
But how does the less water would contribute in increasing the productivity?
Now let me get back to the condition that you are standing in the kitchen and you have one of the pots there, the cooking material, one of the cooking pots, and you need to heat water. Suppose that you are going to put preparing some tea or coffee, and then you have a container, الأبريق or whatever, and you put 1 cup of water there for heating, and you put it on the stove. Versus you filled it all with water and you put it on the stove. Which one of them will be heated faster?
The one with small amount, of course.
That's exactly is the case. There's an amount which is coming here, and this amount is used to heat a small quantity of water. Suppose that I'm talking about the energy coming from the stove as Q.
Yeah, but
and Q is M Cp delta T. Then if the M is small, the delta T will be high. Accordingly, you can reach higher temperature.
cool.
Did I answer your question?
Yes, thank you, Doctor.
Okay, Abdullah?
Doctor, the GOR, how can we calculate here?
The GOR for this unit and for any other unit is basically the quantity of M distillate, the fresh water that we get, into the latent heat needed for evaporation or condensation of the vapor, divided by the Qn. The Qn here is going to be the G times the area. Qn for the whole unit. The whole unit is receiving energy from one source, which is the solar energy. Suppose that you are talking about an active solar still, and you have an electric heater that you are putting here. Then Q is going to be this GA plus Q from the heater. If you have a solar collector, then Q from the solar collector. So whatever energy is used to heat the water is going to be considered here in our Qn. And this is going to be the expression of the Gore for any thermal desalination system.
اوكي.
داود.
السلام عليكم دكتور.
عليكم
بالنسبة
السلام.
للموية اللي انت قلت انه هو اختياري، يعني هل نكتبه
لا.
ولا ما نكتبه؟ لانه انت قصدك درجات في الهوم وورك.
تاني سؤالك تاني يا داود.
اللوز في الموية هو from the side، يعني هل
from the side it's لو انا ما حددتش what are the possibilities of water losing heat from the sides, you don't have to put it. I'm sure الدرجات اللي نقصتها انت ما كانتش بسبب الووتر from the side. It would be something else. Maybe ما كانش فيه absorber plate and you neglected it, but when it comes to the sides, that's not the issue. It's too small.
اوكي. بعدين دكتور عندي سؤال ثاني بالنسبة للترتيب how يعني نرفع البرفورمانس. على حسب الكويز كان عندنا حاجة إضافية اللي هي إضافة لون للموية.
نعم.
عند المسافة بين الجلاس والواتر.
نعم.
ممكن تعيد ترتيبها لينا يعني عشان عندي confusing شوية فيها.
طيب في الحالة دي بعد الثلاثة دول after the less quantity of water, high heat transfer coefficient by convection to cool the glass, radiation higher or lower, number 4, it will be coloring the water, because you are going to color the water with dark dye, and accordingly it is going to have higher absorptivity. And finally comes the distance between the surface of the water to the surface of the glass, because this is going to affect the convection heat transfer coefficient from water to the glass, and the contribution of this term is small anyway. So any enhancement here is not going to be significant.
اوكي. طب اخيرا دكتور في برضه اللوسز اوف واتر نحن ما كتبنا الكيو فروم كونفكشن، كتبناه اللي هو بالنيوتن لو. هل المفترض دائما نكتبه بنيوتن لو ولا عادي لو كتبناه كيو فروم واتر؟
If I requested it to be written in details, for example, write expressions of the heat transfer rates, then you can write it in Newton law of cooling. If I don't request it, then it's fine.
Okay, thank you.
Saleh?
Doctor, isn't we said that effective cooling of glass cover is the first one to better performance?
Actually, they are comparable. I can swap them, and in order to make it convincing to you, what I may do, I can run the ES program that I wrote for solar still, and I can change both and show it to you. I mean, actually they can swap. You can put effective cooling first or less water first, but both of them are having basically some sort of a similar order of magnitude as far as I remember. And I'll show it. I'll probably post that. I'll make like a parametric study, and I'll show you the effectiveness of doing this and that, like less water or effective cooling of glass. But if you write this or that, both would be fine for me. Okay, now we can move to the next mode, which is basic, or the next technology for desalination, which is basically going to be talking about HDH, or humidification, dehumidification, desalination. In humidification, dehumidification, desalination, the kinds of analysis that will be exposed to is one of two things. One of them, to design a unit, and the other one is to rate a unit or look at the performance of an existing unit. Design the unit, you are going to use figures, like what you have in the first and second problems of the last homework. Then we have figures that are ready. We have basically 3 figures. One of them is for gain output ratio. The second figure is for recovery ratio. And the third figure is going to be for, anybody remembers?
Mass ratio.
Mass flow rate, yes, mass flow rate ratio. So basically, these figures are having an x-axis, which is the effectiveness. I'm not quite sure whether the effectiveness of humidifier or dehumidifier. And the other one is the effectiveness of the other component. So one is the effectiveness of the humidifier, one of the effectiveness of the dehumidifier. So the problem should have the values of the effectiveness for humidifier and dehumidifier given to you. And accordingly, you would be able to know if you are given the distillate flow rate, which is always the case. I mean, we say that we need to design an HDH system that can provide us with the problem in the homework was saying 1 cubic meter per day. أنا محتاج طن من المية الحلوة كل يوم. I would convert that into kilograms per second, and then that becomes our productivity. Then, when I'm calculating based on this epsilon, I calculate the GOR. Again, the GOR, as we mentioned before, this is m dot distillate into HFG divided by QA. HFG is a constant value. So normally, we take it something like 2330 or 2350 or whatever kilojoule per kilogram. So if I know m dot distillate, I know HFG, I know the GOR from the figure, I can get QA. Recovery ratio is m dot distillate that we have divided by m dot seawater n. The distillate quantity is known. The figure gives me the recovery ratio, then I can get m dot seawater. MR is m dot seawater divided by m dot air. So if I know the value of MR, I know the value of seawater that I got from the previous step, then from here I can get the mass flow rate of the air. So this is basically the case, whether we are talking about a water heating or an air heating system. The water heating system has its own figures. The air heating system has its own figures. And then basically this is how we get the basic components, and there will be another parameter if I need to calculate, for example, the surface cross-sectional area of the humidifier. Then we use m dot water over area as the mass flux in the humidifier, and we pick a value of 1.5. You can pick a value between 2 to 4. It's all up to you, but it's just we agreed that this is a reasonable selection. And then I would know the value of m dot water from here, m dot seawater, which is here. I know it, and this is a constant, so I can get the cross-sectional area of the humidifier. So this is how we determine the dimension. And then we go to another figure that is going to give me the height of the packing material based on the maximum temperature, which basically, because these figures were made for a maximum temperature of 60, so in most of the cases, you'll be asked to deal with it for a case of maximum temperature of 60. If the maximum temperature of the system is different, then we have to provide you with the figures that are suitable for that. Then you calculate the height of the humidifier. Then there's another equation based on the overall heat transfer coefficient, which is given to you. You can calculate what is the surface area for the dehumidifier, whether it is based on water heating or air heating, and then you can get the value. So we're talking about some sort of standard steps that you are going to follow in order to do a thermal design of the unit. Differences here, I mean, I can expect when I'm asking you to come up with a design for an HDH system that I'm giving, I would have results that are not similar, because there's a human factor when you get a value here and a value of the figure, And this value, somebody can calculate the GOR as 1.9, another one calculated as 1.95, 2 or 1.8, something like that is acceptable as a tolerance in the solution. So I don't expect, and you are not requested to provide an exact number, because that's something, for example, somebody have a figure like this, and you got the point of intersection here, and you need to move to the left. Somebody would do it like that. Somebody is going to do the left is like this, the left is like that. So, or each one of them, somebody would consider it visually as a horizontal line. So that's the kind of, based on the scale that we have. So this kind of variations that can be expected in a system like that. What is more important is how you are following the procedure for the analysis.
Doctor?
Yes.
Yeah, so for the surface area of the, I believe there is a figure to find out, to calculate the, or to approximate the surface area. Is it for the humidifier or for the dehumidifier?
It is for the dehumidifier. Surface area, then it's for the dehumidifier. The humidifier, you have to calculate the cross-sectional area and the height of the packing material. That's all. We cannot do more about this.
So 1.5 represents the height of the material, right?
No, 1.5 represents what we call the mass flux.
Mass flux.
The mass flow rate divided by the cross-sectional area.
I see.
This number came from the analysis of the cooling towers. You use this to calculate the surface area. But the height, this is something else. It is based on the effectiveness that you have. It is based on the temperatures that you have. And you can see what is the best height of the packing material. There's a figure for that. But there's no figure for the area. We use that expression.
All right, thank you.
You're welcome. Now, the second kind of problems that you can have dealing with HDH systems is the rating problems. You have an existing problem and you need to do an analysis of the performance. In that case, Muhammad Al-Gham, do you have a question?
Yes, doctor. What about the formula that NTU equal U A surface over C minimum?
It's another way to calculate the surface area. So the surface area can be calculated from a figure right away, or can be calculated based on the number of transfer units and the specific heat ratio, which is the capacitance ratio. You can do this or that. It's easier to do it directly as area of the dehumidifier based on this. Otherwise, the number of transfer unit is an overall heat transfer coefficient multiplied by the area divided by C min. What is C min? This is basically M dot Cp minimum. We have two fluids. We have water and air. You calculate M dot Cp for the water, M dot Cp for the air, and you take the lower value. This is your C min. The overall heat transfer coefficient would be given to you. The number of transfer units, you can get it from the figure, then you can calculate the area.
So you will be, if the figure is not given, I can use this formula and we'll get same number.
Yes, it's basically given the same number, but normally the value of the overall heat transfer coefficient is given to you because calculating it is a little bit involved, that you have to go for forced convection inside the tubes and a kind of condensation on the outside surface of the tube. So the correlations, it would be some sort of a lengthy process, which is not the target. The target is to come up of how to calculate the surface area. That's something probably we can ask in a project, that you can calculate the details of the overall heat transfer coefficient. Did I answer your question, Isalah?
Yes, Muhammad.
The thing here which would be considered is when I'm talking about a rating problem. Rating, it means that I do have the components, a dehumidifier and a heater. And the information will be given to you in a way, like what you have seen in the quiz, that the needed values of the enthalpies are always given. I'm not going to ask you to go for the psychrometric chart or even go to the existing softwares on the internet to calculate H for humid system, for humid air. That will be given to you always. what you would be expected to do is to be able to run the energy balance and mass balance, of course, for the system. The only mass balance that we would have, now I'm talking about a water heated system, is that m dot water coming to the humidifier is going to be basically m dot brine plus vapor, which will be carried by the air. So the kind of mass balance that we have here is that m dot water entering will be m dot brine rejected plus m dot evaporated. Sorry. The m dot evaporated is going to be the quantity of water vapor carried by the air, which is m dot air into the difference of omega between points 2 and point 1. So we have here air coming in at state number 1 and air leaving at state number 2. So omega 2 minus omega 1 is the difference in humidity that of the air, and this is basically the quantity of water vapor carried by the air that's going to define m dot evaporated. So this is the mass balance equation. Other than that, the equations that would be required are basically the energy balance, and the effectiveness expression. Energy balance, if I'm talking about a humidifier, then let's look at the components. We have air coming in, so m dot air into H1. We have water coming in, m dot water, H water. Let's call this 3. This is the energy in. The energy out is going to be m dot air, H air 2, and m dot water, H brine. And I have to tell you here that whenever we are talking about water, it is an acceptable approximation to put this H as Cp into temperature. It is not very accurate because the way Cp into temperature has been basically created for a difference of energy, like delta H, for example, is m dot Cp delta T. But the expression of Cp into the temperature can approximately be accepted as a way to represent the energy of the water, provided that you are sitting in an exam and you don't have softwares that you are going to, or table that you put the value of the temperature and it will give you the enthalpy or vice versa. So Cp into T can be acceptable then. This is the energy out and this is the energy in. So this is the energy balance for the humidifier. As I said, always the values of H will be given to you. Sometimes we hide one of these values of the H's. It is not given and you are asked to calculate it. Asking to calculate it, which means that you are going to deal with the effectiveness expression. And we have effectiveness based on the water side or the air side. If you noticed in the quiz that I've specified that this is effectiveness of the air side so that you don't have to write both of them and search which one is the highest because some of them will not be given. So when I'm saying, for example, effectiveness, you are given effectiveness for the air side for the humidifier, then this is basically going to be H air outlet minus H air inlet divided by H air outlet ideal. So let me put it this way, H air ideal minus H air 1. H air ideal, this is the ideal condition for the enthalpy of air, as if air is being heated here to the maximum temperature, which is this. So this is basically H of air at a temperature equal to T water 3. And this is also given to you. So if the effectiveness is given and this value is given, HA1 is given, then I can ask for the value of H2, which you can obtain it easily here, which is for the air leaving the humidifier and going into the dehumidifier. The same thing can be done. If, for example, I can probably not provide you with the T water leaving here, but rather I would ask you to calculate this value. Maybe you can calculate H water out from here and then substitute into this equation to get H of the brine. So that's something that can be done in problems. So that each time in one equation, you have only one unknown. What I want to make sure here, or to make it clear, is that you are always be having an equation, and the equation is going to have only one unknown. The effectiveness expression here, you can use this expression to get enthalpy of the air leaving the unit. Then make use of the enthalpy expression here to substitute it into the energy balance and calculate, for example, what is the enthalpy of brine leaving. What about the quantity of brine? If here that, to be more accurate, this is m dot brine, and m dot brine is going to be m dot water, which is always given minus m dot evaporated. What's m dot evaporated? It is m air into the difference in omega. So this is as far as the balance or the energy balance for the humidifier is made. If I want to look at the other component, yes, ya Khalid?
Yes, Doctor. A question here. If would it be the formula for the effectiveness, whether it's for the humidifier or the dehumidifier, be different?
I'm going to that. Yes, I'll be talking about this in a while.
If we change the system, like open water, closed water, that's all.
Actually, when it is open water or closed water, that does not make a difference in the effectiveness expression. Values would be different, yes, but the effectiveness is what? Is not. The point here is, now I'm talking about m dot evaporated. Is the m dot evaporated as the same as m dot distillate?
Yes.
It would be if it's a closed air system. If it's not a closed air system, then it's not. And probably the problem, is it the problem of the homework that you have an open air system in which you have the two units here. Here air is coming from outside, so it has its own enthalpy. And this is the air. When it's humidified, it's going to enter, which is in H air 2. And what we have here, air, it's not a closed loop, but we are throwing the air away. So m dot evaporator here is going to be m dot air into omega 2 minus omega 1. But m dot distillate is the difference here across this unit. So it will be m dot air into omega 2 minus omega 3. So this value and this value are not the same. It's not a closed loop of the air. You are extracting air from the atmosphere and you are throwing air to the atmosphere, and it's not a closed loop. In that case, the condition of omega 1 and omega 3 are not the same. So this is what you need to be aware of while you are looking at the problem. Am I talking about a closed air system cycle or an open air cycle? I hope I did answer your question, Khalid.
Yes, Doctor. But again, you said there is no difference if it's for the effectiveness.
There's no difference in the expression of the effectiveness. As long as I'm talking about water heating cycle, and the water enters here hot, and the air enters as cold, then the effectiveness is not going to change, whether it is an open system for the air or closed system for the air. Water is hot and air is cold. So always the effectiveness is going to be this expression.
How about the heating system? If we change it from water heated to air heated,
this is going to make a difference here. When I'm talking about a humidifier of an air heated system, then that's a little bit different. Why? Because the hot fluid is the air and the cold fluid is the water here. So let's put this in which I'm using air and the air is passing by a heater inside. And this is air 1. And then it will leave here as air 2. And it will enter to the dehumidifier and leave it as air 3. Again, the value of the evaporated value versus the condensed values are not the same, because this is omega 2, this is omega 1, and this is omega 3. And when I'm looking at the effectiveness of the humidifier here, the natural difference is basically going to be H air 2 minus H air 1. What about the maximum difference? The air, what happens to the air here? Is it heated or cooled down?
Cool down.
It is cooled down because water is colder. So air will be cooled down, which means that actually the way I should put that equation, actually this should have been H1 minus H2, because air comes as hot and it will leave as a cold value. Then this air is entering at H air 1. This is coming from the heater, so this is not going to change. But the humidifier is going to cool down the air. What is the lowest temperature that the air will be cooled down to?
Water inlet.
Water inlet, which will be this. So this is H air at water inlet. Definitely when water is sprayed, water is going to be taking some energy from the air and it will leave here as m dot brine at T brine, and T brine is going to be greater than T2. Because basically air is hot in this case. So that would be how I write the expression of the effectiveness. Again, when you're looking at the effectiveness, you are looking at the actual enthalpy difference of the fluid that you are considering divided by the maximum difference. If the air is being heated, I look for what is the maximum temperature in the condition in the unit here, and I'm going to consider the enthalpy of air there. If air is being cooled down, I'm going to look at what is the minimum temperature here, where air ideally is going to be cooled down from its maximum value at the inlet to the lowest value, which is this. So that in the denominator for this one and this one, basically what I'm looking for is delta H maximum. Okay?
All right.
Now, let's look at the dehumidifier. And for the dehumidifier, I'm going to write, again, the mass balance and the energy balance, and then the expression of the effectiveness. And again, you might be given the value of the effectiveness, then you are going to make use of it to calculate some sort of an enthalpy. The other enthalpy that needs to be calculated is going to be calculated from the energy balance. So always, you're going to have your system in a way that you have only one unknown per step. So now let's consider the dehumidifier. It is receiving air at 2, returning air at 1, and then this is water here coming as water 1, leaving water 2, and this is water 3, and there is distillate which is leaving here. Now the effectiveness of the dehumidifier in the air side, actual difference in enthalpy, which is H air 2 minus H air 1. If it's an open system, it will be H air 2 minus H air 3, which is the actual difference of enthalpy across the dehumidifier divided by delta H maximum. H air 2 here is coming with with a certain known value, which is what is going to happen here? Air is going to be cooled down, so it will be the inlet condition as is, and air is going to be cooled to the lowest temperature, if I'm talking about 100% ideal situation, which is the inlet water temperature. So this is going to be H air at T water 1. So this is going to be the effectiveness expression. If I'm looking for the energy balance, then the way I prefer it also is the energy N, which is m dot air, H air 2. Water is entering, so have m dot water, H water 1. This is what comes into the unit, to the dehumidifier. What leaves the humidifier is m dot air, H air 1 if it's a closed system, and H air 3 if it's an open system, plus m dot water, H water 2. Water has heated a little bit by gaining energy from the condensing air. And there is distillate which is leaving, H distillate. Normally the value of H distillate will be given to you, unless this is what we are looking for. You are given all the values and we need the value of HD. But otherwise, the H distillate would be given to you. And the m dot distillate is going to be basically m dot air into the difference of omega across the units. So it will be omega 2 minus omega 1 for a closed system, omega 2 minus omega 3 for an open air system. So problems related to the HDH in terms of rating will be something similar to what I've shown here. The only difference that I did not talk about is going to be in case of we have air heating after it leaves the humidifier, which is the modified air heating cycle. And for this cycle, there is some difference here, that a piece of information that we don't give to you because we assume that you should know it. And that normally becomes, in some cases, the trick of the problem, which is the kind of heating that happens in an air heater is sensible heating, which means that I think the problem that we have, so the example that we have solved in class was of that kind. I'm talking about a humidifier, and then a heater, an air heater. So the air is being heated here. So this is air at state 2. And then this is leaving at air at state 3, which is at a higher temperature. And this is the humidifier. This is the dehumidifier. And then the air gets back here if I'm talking about a closed system. Water is going to enter here, water 1. Water 2 is going to enter here. And here we have the brine rejected, or water 3, if you want to call it this way. So what would happen here is that across the heater, heating is sensible heating only. Remember that. Which means that omega 2 and omega 3 are the same. This is a key for solving this problem. That the mass of the water vapor carried by the air did not change. I heated it, but I did not add by condensation. I did not take something out by evaporation. This is only sensible heating for the air. Definitely phi is not. Because phi is a function of omega and temperature, and the temperature definitely is different. But the key for solving this kind of equation of modified air heating is that across the air heater, the value of omega is constant. It is not changing. So when you find you have a problem like this, I may give you the value of omega 2, and would not mention anything about omega-3, and probably tell you here that we are going to heat it to a value of Tmax equal to maybe 80 degrees centigrade. When you look at the problem statement, you'll find that at state number 3, you are having only one property, which is basically not enough. But this is made based on that you would know that the value of omega across the heater is constant and it is not changing. So this is basically the kind of tricks that you can see in an HDH problem. I'm afraid the time has already ended and we don't have time to talk about the single effect evaporation, but we have already gone through an example for the single effect evaporation. Right now, after the class, I'm going to post the book of Ad-Dasuqi and Ad-Tuni on saltwater desalination, and you'll find in that book that chapter 2 is dedicated to single effect evaporation. It has example and it has end of the chapter maybe a kind of 3 or 4 problems that if you need to practice on that, you can do that.
Thank you so much, Doctor, for that effective revision.
Doctor, the time for the midterm.
Oh yes, I'm glad that you brought this point up. There's one suggestion that we can start in the class time so that you can make use of the early morning while you are fresh. If you all agree on that, which is fine with me, then but we have to log in not 8:30, but we have to log in at 8 o'clock because we need to make sure that I will just take the attendance properly. You are going to adjust the cameras, and I make sure that everyone of you is having the right position of the camera. I sent you an email at the end of our last quiz indicating who's having a good posture or position of the camera and who have something hidden. So that I want you to follow what is the best technique over there. So to make sure of that, we'll need this first 30 minutes to make adjustments for the setting. So if it's fine with you to start at 8, so that our quiz is going to start at whenever we are ready, 8:15, 8:20, 8:30, and it will be for 1.5 hours. It will be 3 problems, one on the solar still, one on the HDH system, and one on the single effect evaporation. If it's fine, whoever is agreeing on that, you can please check yes, which is down there below your names. Anybody has a problem with this? Definitely, it will be in no conflict with any other exam or other material. So, Abbas Al-Yahya, are you with us? Abdul Karim, Ahmed Al-Hussein, Dawood Al-Haji, Hussein Al-Yusuf, Usama Shah. I just want to make sure that I did not see you checking it, so I just want to make sure that
I don't know where it is, Doctor.
So at least Hussein, I know that it's fine with you. Usama already has raised his hand. Abbas Al-Yahya, you can either raise your hand or check the yes mark. Okay, and Abdul Karim, you said it. Abdul Karim, is that fine with you?
Yeah, I'm here.
Fine. So, and Hussein Al-Yusuf, he said it's so fine. So we are going to meet. I think we have maybe someone is missing today. Actually, 2. So we need them. I'll compare the report sheet of the attendance of this of the class with the class roster to know who's missing. But we need to make sure that everyone knows that we are going to log in at that time. So it will be 8 o'clock on Wednesday, inshallah. I'm going to post the book. So please, today, sometime after maybe half an hour from now, you can check and find it there. It's a PDF file. The size is a little bit big. It's about 25 megabytes, but you should be able to open it easily, inshallah.
Doctor.
Yes.
Can you upload the solution for quiz 2 for any version?
Oh, for quiz 2, fine. I'll pick up one version and I'm going to solve it and put it in detail so that it becomes self-explanatory. And hopefully for any version which is different than that, you can just put your number in and then you're going to have the correct answer. Yes, I'm going to do that today, inshallah.
Thank you.
دكتور معلش عندي سؤال.
Yes?
بالنسبة لو طلب مننا التي فور اير كيف حنطلعه؟ زي سؤال الهوم ورك.
الهوم ورك you have EES, or you have if you look at the internet and you Google for psychrometric calculator, you will get something where you can get it from there. You are sitting at home, you have your time so that you can look for the property. This is something which is not there in the exam. So in the exam, I can ask you for the temperature of water, but not the temperature of air.
Okay.
I would provide you with a link to a software you get into the internet where you, for example, you put the value of H and you put the value of either the relative humidity or the humidity ratio, and then the software will be giving you the value of T, which doesn't make much sense if I'm talking about an exam problem. Okay, so inshallah we'll see you on Wednesday, Shabab. Inshallah. Yes, Saleh, تفضل.
The figures for design HDH.
Yes.
They will be similar to the exam, or?
Yeah, they will be provided to you. They are the same figures, by the way, or something similar if the temperature is different. But more or less, it will be the same as you have.
So I can print it to use it.
You can print it, yes.
Doctor?
Yes.
Can you please upload also an exam and solve an example for the single effect evaporate?
Yes, I will. And you will find one in the book, which is given in details. And the example that we have solved, I can make sure I can post it as well.
Okay.
Inshallah. So sometime today you should be able to see it, yani, inshallah.
Thank you.
Yeah, you're welcome. Okay, Shabab. So we'll see you on Wednesday, inshallah.